In this video, we are going to cover Chapter 11, where we discuss gases and their properties. Now, what do we know? We know that gases are very compressible, they have low density, and if we were to put several gases together, they mix thoroughly. We are going to analyze 4 properties of gases and see what effect they have on the physical behavior of the gas. You guys are familiar with those. So we have, for example, the excuse me, the volume of a gas. And whenever we talk about the volume of a gas, we're actually discussing the volume of the container, since gases do completely fill their container. The amount of a gas, and that would be the number of particles in there, and we're going to measure those in moles. Then we are going to use the kinetic energy of a gas. And since kinetic energy is directly proportional to temperature, we are going to be looking at the temperature of the sample. And since we're looking for kinetic energy must be positive at all time. Therefore, we need a temperature scale that is always positive, and that would be Kelvin. So the temperature is always in Kelvin. So let me reiterate this one more time here. I have always underlined. That means no matter what, you need to convert temperature to Kelvin at all times. Then we have pressure, which tells us that anytime you have a gas, that gas is exerting pressure uniformly on all sides of the container. We'll come back and discuss what pressure is. But first, let us take a look at the model that we're going to be using to describe the behavior of the gas. And that model is the kinetic molecular theory, which is going to help us understand the behavior of the gas. Now, this model is going to be used based on the conditions we are looking at. Now take a look at the name. The name right here says kinetic. That means we're going to be looking at the kinetic energy, and molecular. That means the nature of the molecule. So we're going to be using kinetic and molecular. And so now that model works under certain conditions, and we'll discuss later on in the chapter what conditions this model will not work. So the 4 tenets of this model that we have here are going to be that a gas is a collection of particles that are constantly moving. They're never at rest. So, all right, so they're in constant movement. While they're in constant movement, they don't attract each other. Okay, so even when they pass by each other, there's no attraction or repulsion between them. In other words, we're saying there's no loss of energy in between these. And when they come very close and collide, the collisions between them are elastic collisions. In other words, there's no loss of energy. When they collide, they transfer energy, but they never lose energy. For example, when you use the cue ball in a billiard game, where when it hits one ball, hits the other one, it transfers the energy and it causes it to move. That's the type of collisions we're talking about. If you recall, we said there is a lot of space between the particles, and this is what causes them to have a low density, for example. That's why they mix thoroughly. That's why they're highly compressible, because there is a plenty of space between the particles. And last, when we talk about the average kinetic energy, we say that that kinetic energy is directly proportional to the temperature in Kelvin. Now, since kinetic energy is 1/2 mv squared, and which equals, so that is the mass and this is the speed, 3/2 RT. That's the temperature. So higher temperature, it means particles are moving faster. That's basically what this is saying. All right, so the particles will move faster at higher temperature. I already told you all these things. The low density, the mixing, the compressibility, and because they move fast and they're constantly moving, they will always occupy the whole volume of whatever container they're in. And because there is a plenty of space between them, they will mix thoroughly. Now let's talk about the property pressure. Now, pressure is defined as force per unit area. All right, so we define a pressure as force per unit area. So whenever we're talking about the pressure of a gas, we're talking about the force that the pressure is the gaseous molecules are exerting on the surface. So if you're here, then you'll see all those particles bombarding all surfaces. If we sum up all the forces divided by the surface area of this container, we end up with the pressure. So you can imagine that if I double up the amount of particles in there, I end up with high pressure. Or if I take this same amount of particles here and put them in a smaller container, I'm going to get high pressure. All right. So we're going to explore the different factors that are going to affect the pressure of a gas. But first, let's define some units of a pressure. Okay. We go back to saying that pressure is a force per unit area. Unit for force is Newton, area meter square. So Newton per meter square is defined as Pascal. Okay, so the SI unit for pressure is Pascal. Let's see if we can define some other units. Let's imagine that, the atmosphere, our atmosphere, to consider it as a huge reservoir of gas, and that gas, as in here, is going to be exerting pressure on the surface of the Earth, right? So if I were to construct a contraption like this, where you can put liquid right here, and in order to make this work, we're going to use mercury, since mercury has super high density, so we don't need a big contraption. We can use a small contraption. And I'll use a vacuum tube right here. So as the air molecules bombard the surface of this liquid right here, they're gonna cause the liquid to rise inside the tube. Now this liquid is gonna rise until we have enough liquid in there that its weight is gonna exert the same force as the force exerted by the air particles from the atmosphere. Once that weight from here is exerted equal to the force here, then the liquid stops. Now think about it. The weight is the same as force, right? And it is per unit area right here. And that means the pressure. So the pressure exerted by the liquid inside equals the pressure of the atmosphere. If we were to measure the height of that liquid, we can come up with a way to measure the atmospheric pressure. We call this setup a barometer. And usually we measure it in millimeters of mercury. So at sea level, the pressure of the atmosphere is 760 millimeters of mercury. We're gonna define that as the unit atmosphere. So 1 atm is roughly 760. Now, why do I say roughly? I know your textbook says it's exact. It is not, because mercury is a metal and metals expand due to different temperatures. Therefore, it is not exact. So it depends on what the temperature is. So we need a temperature correction factor. So we can define another pressure unit. We're going to call it the torr. That torr is exactly 1 atm 760 torr. So this one takes into account the temperature correction. Another pressure unit, which you guys are familiar with, is the PSI. That will be pounds per square inch. 1 atm is 14.7 PSI. Again, let me remind you, the official SI unit is the Pascal. So 1 atm is 101,325 Pascal. Another SI unit is the bar. much more manageable unit, and that would be 1 ATM is 1.01325 bar. You should be able to convert between these units fairly easily. You guys know how to do dimensional analysis, so let me give you an example. Let's say we have a high performance road bicycle tire and is inflated to a total pressure of 125 psi. What's this pressure in millimeter of mercury? So we're given 125 psi and we want to convert it to millimeters of mercury. So I want to go from psi to atm, then from atm to millimeter of mercury. Since this table right here, it shows us how everything is related to atm. So it behooves us to convert to atm first, then go from atm to the other units. And the relationships I'm going to use from that table will be 1 atm is 14.7 psi and 1 ntm is 760 millimeters of mercury. So I can go from psi to atm by using the following conversion factors. Since I'm starting with psi, I want psi to be in the denominator. This, this will give me units in atm. Then I want to go from atm to millimeter of mercury, so I'm going to take, excuse me, this conversion factor right here, 1 ATM equals 760. Since I'm starting with ATM, I want ATM to be in the denominator, and I put 760 millimeter in the numerator. So then I'll set it up as such. 125 psi times 1 ATM over 14.7 psi. This will allow me to cancel psi. Then I multiply that by the second conversion factor times 760 millimeter mercury over 1 ATM. And this will give me 6.46 times 10 to the 3 millimeters of mercury. That would be the answer. Now our answer is reasonable. Since millimeter of mercury is much larger unit than psi, we should get a larger number. All right, now you try this one. Pause the video, then look at the answer. All right, so we're going from PSI to kilopascal. That means I should go from PSI to ATM, from ATM to kilopascal. And these are the relationship that I'm going to use. Same thing. Then we set it up as follow. 45.5 PSI times 1 ATM with 14.7 PSI will allow me to convert to ATM. Then when ATM equals 101.325 kilopascal, so I end up with 314 kilopascal. You can consult these problems for more practice in your textbook on this stuff. As I told you, now that we have defined the different characteristics and properties of gas, that we're going to look at their effect on the physical properties of gas, or physical behavior rather of gas. Now that we've defined them, let's go on and look at how they're gonna work. So the way we're gonna do this, since there are 4 of them, we're gonna hold 2 constant and change one and see how the other one responds. The first, we are going to hold temperature and the amount of gas constant. Then we're going to look at how does the pressure change and change to volume, or how does the volume change and respond to change in the pressure. This work was done by Boyle, therefore the outcome is called Boyle's law. So if we were to take a sample at constant temperature and number of particles, then change the pressure, we're going to end up with changing in volume. If we were to plot that data, we can end up with something like this, right? Larger pressure at high pressure, our volume is going to decrease, and at low pressure, our volume will increase. This tells us that the volume is inversely proportional to the pressure, right? Volume is inversely proportional to the pressure. If we were to take that data and instead of plotting it volume versus pressure, we can plot it as a pressure against the inverse of the volume, Okay, pressure against the inverse of the volume, I end up with a straight line. Perfect. That straight line will have y equals mx plus b. In this case, b, the y-intercept is 0, right? Because at 0 pressure, I have no volume, and at 0 volume, I got no pressure. So the y-intercept is b, x is 1 over v, and y is the pressure. Equal the slope right here. So if I were to take x, multiply it by y, I get, or 1 over x, multiply it by y, I get the slope. Let me share what I'm talking about here. Y we already established that b is 0, y is the pressure, and this is the slope m, and x is 1 over v. I'm going to rearrange this. So that would be P times 1 over V equals M, which equals P times V equals a constant. And since the slope is constant, that means no matter what the value of P is, it will have a V that corresponds to it, right? You can pick any value right here, any value, and find the corresponding V, and they constantly change. That means P1 times V1, this point, I can take this point right here, another one. They're going to be equal because they all equal that slope, right? That will mean P2 times V2, and so on and so forth. I can do that all the time, and that is called Boyle's law. All right? P1 V1 equals P2 V2. That is Boyle's law. Let's take a look at how we can apply Boyle's law. A cylinder equipped with a movable piston has an applied pressure of 4 atm and a volume of 6 liter. So that's my P1, 4 atm, and V1 is 6 liter. What's the volume of the cylinder? So I don't know what V2 is. I know what P2 is 1 atm. So I decrease my P2 to 1 atm. I need to find V2. I'm gonna use Boyle's law, right? I'm gonna go from, I have P1, V1, and P2. All I need is V2. That means that Boyle's law needs to be arranged. So I'm gonna rearrange Boyle's law as such to isolate V2 on one side, and all I have to do is plug in the values. You get 24 liters. As simple as that. That's how it works. Let's look at another example. A balloon is put in a bell jar and the pressure is reduced from 782 torr to 0.5 atm. The volume of the balloon is now to 2780 milliliter. What was it originally? Go ahead and pause the video, try to work this one out, then come back and check your answer. Let's organize the information. V2 is 2780, P1 782 torr, and P2 0.5 atm. I'm looking for V1. Right off the bat, you notice that my pressures are not the same. That means I need to convert one into the other's units in order to be consistent. I can't use the pressure that way. I have to change it. So I'm going to use Boyle's law and I'm going to convert the pressure. Since I'm looking for V1, I'm going to rearrange the equation as such. P2 times V2 over P1. And let me change P1 into ATM. 782 torr times 1 atm over 760 torr will give me 1.03 atm. So I converted that to atm. Now all I have to do is plug it into the rearranged Boyle's equation, plug in the values, and end up with 1350 milliliter. Let's check out our answer, see if it makes sense. Our pressure is reduced If the pressure goes down, the volume has to go up. All right? So my volume is going from, since pressure and volume are inversely proportional, I went from 1.03 atm, that's P2, that's my P2, so my pressure is greater than, the pressure is reduced from 7 to 0.5. So 0.5 is my P2, so my pressure went down. If my pressure went down, my volume should go up, and it does, 2780, right? That's V2. So the original volume is less than the volume we're gonna get, so it makes sense. For more practice, you can actually check out these problems, guys. The second law we're gonna look at is Charles' law, where we compare temperature and volume while keeping pressure and number of particles constant. All right, so let's take a look at the following. If I were to take a balloon and fill it with gas, that balloon is gonna, the pressure is gonna stay constant because it's expandable. It changes volume in order to make the pressure the same. So if I were to put that balloon in an ice bath, it will shrink. It'll shrink in order to equalize the pressure with the atmosphere. By doing so, that means at low temperature, the volume is going to go down. The pressure stays constant. If I were to take the same balloon and put it in a hot bath, it will expand because the pressure on the inside increases so much so, then the volume has to expand in order to equalize the pressure with the atmosphere. So volume and temperature are directly proportional. If we were to plot volume versus temperature for different conditions, right, we can change the identity of the gas or the amount of the gas, the amount of pressure. It will always give us a very similar pattern, right? Volume is directly proportional to temperature. And if we were to extrapolate, now if we look at this, we can say that volume equals a temperature times a constant. Okay, temperature times a constant, since the slope is a constant here, so we can do that. In addition, if we were to extrapolate all these lines, they'll lead us all back to a single point, to negative 273.15 degrees Celsius, which is known as the absolute zero. That zero right there is 0 Kelvin. And Charles' law will be rewritten as V1 over T1 equals V2 over T2 as long as the pressure and number of particles N are constant. Keep in mind, temperature must always be in Kelvin. Let's take a look at an example. A sample of a gas has a volume of 2.8 liter at an unknown temperature. When the sample is submerged in ice water at T equals 0, its volume decreases to 2.57 liter. What's its initial temperature? Both in Kelvin and in Celsius. Assume a constant pressure. Let's organize the information that we have. We have V1, V2, and T2. We're looking for T1. So I'm going to use Charles' law. I'm going to rearrange it to isolate T1 on one side. Then, since I'm using T2 here and it was given to us in Celsius, I need to convert it to Kelvin. So I'm going to add 273 to it. That's in Kelvin. Then I'm going to plug it into the equation. And I end up with 297. That's in Kelvin, but the problem or the temperature was given to us in Celsius. I need to convert it back to Celsius. So I subtract 273 from my answer and I get 24 degrees Celsius. All right, your turn. Try the following. Pause the video, try this, then come back and check the answer. The temperature inside a balloon is raised from 25 to 250. If the volume of cold air was 10 liters, what's the volume of hot air? So I have V1, I have T1 and T2. I am looking for V2. Okay, so I'm going to use Charles' law. I'm going to rearrange it to give me V2 equals V1 times T2 over T1. The temperatures are given to me both in Celsius, so I need to convert them to Kelvin. So let's convert both temperatures. So I'm going to add 273 to both. I get them in Kelvin. Then I plug in into the rearranged equation. Make sure that you label your parameters that you're given correctly to begin with, so you don't make a mistake. So we get 17.5 liters. That is Charles' law. We can take Charles' law and Boyle's law and combine them into what's known as the combined gas law. P1 times V1 over T1 equals P2 times V2 over T2. In this case, N is constant. Let's take a look at an example. How would we apply the combined gas law? A sample of gas has an initial volume of 158 milliliter at a pressure of 735 millimeter mercury and a temperature of 34 degrees Celsius. If the gas is compressed to a volume of 108 and heated to a temperature of 85, what's the final pressure in millimeters of mercury? So let me organize the data that we're given. So we're given P1 735 millimeter of mercury to start with. My initial volume, that's V1, 158 milliliter, and the initial temperature is 34 degrees Celsius. So that's T1, V1, and that's P1. Then the sample is heated to 85 degrees, that's T2, and compressed to 108 milliliter, that's V2. So now I have all the information. I am looking for P2. So I'm going to use the combined gas law to go from the data that I'm given to P2. Actually, let me show you how you can rearrange that equation. Then I'll erase it and we can do this. So we go P1 V1 over T1 equal P2 V2 over T2. What I want is to isolate P2, right? So I'm going to multiply this side by T1 over V2, T2 over V2. Then I have to multiply this side by T2 over V2. This would allow me to cancel V2, V2, T2, T2. I end up with P2 only. So P2 equals T2 times P1 V1 over V2 T1. That's how you rearrange that equation. So we end up with P1 V1 T2 over T1 V2. That's how we arrange this equation. The temperatures are given to us in Celsius, so we need to add 273 to each to convert it to Kelvin. Then we simply plug into this equation right here all the values we got up there with the converted temperature. We end up with 1.25 times 10 to the 3 millimeters of mercury. All right, now your turn. Try the following. Pause the video, then come back and check your answer. All right, so let me organize the information. We are given V1, T1 and P1, T2 and P2. We're missing V2. We're looking to find V2 in this case. So I'm going to rearrange the equation to isolate V2 on one side. It will give me the following. Temperature must be converted to Kelvin. It's given to us in Celsius. So let me convert my temperature. We convert it to Kelvin. Then we plug in into the rearranged equation. We end up with 27.3 liters. You can practice more with these problems right here.